You all can hear me, right? Okay. So I just moved my office next to Dr. Norman Zaimin, the Deputy Dean's office. Yeah. So it's next to the Dean's office. So probably I cannot shout like before. That's why I purposely borrowed a microphone from Dr. Amir for this class. Yeah? So I can speak in a medium, I guess, not so loud, but hopefully all of you can hear me. Yeah. So there's the four methods that we're looking into: method 1, 2, 3, and 4. Yeah. And then from there we look into the concept of feedback uh, control. Yeah. And we look into the advantages and disadvantages of feedback control systems. And then for feedback, also we have feed-forward control. Yeah. And then finally, we talk about or discuss on the justifications of process control. Yeah. So what are the justifications of process control? Yeah. So we have as many as 1, 2, 3, 4, 5, 6, 8, 9 specific objective of control here. Yeah. Starting from increased product throughput, increased yield of higher valued products, decreased energy consumptions, decreased pollution, decreased off-spec product, increased safety, extended life of equipment, improve operability, decrease production labor. Yeah? So the 9 specific objectives of control. And if we interpret that quantitatively, yeah, through some qualitative results as shown as the graph here, yeah, we look into how before control and after control. Yeah? So we minimize the number of off-spec products when we apply control as influenced by these two graphs here, before A and after control system applied B. Okay? And this is the distribution, the Gaussian type distribution. So you can see here that after you applied control, the range become narrow. Yeah. When we have control systems in place. And then we move to the hierarchy of process control systems. Yeah. So starting from, make it bigger here, starting from process, yeah, all the way to starting from process to go to measurement and actuations, and then safety, environment, and equipment protection. Then regulatory control, multi-variables and constraint control, and real-time optimization, and finally planning and scheduling. And all these control activity will have their own time frame, yeah, from less than 1 second for a simple measurement and actuations to probably days to months for planning and scheduling. Yeah. So as far as the control system is concerned, yeah, we are probably put more effort to understand what it means with multi-variable and constraint control, and the real-time optimized sessions. Yeah? And towards management, they will lead to planning and scheduling. Yeah? So what you have learned before together with Dr. Fikri in the earlier part of the course, yeah? Before the MCO, we are more, we discussed a lot about measurements and actuations and the sensors. Yeah? Then we move on safety, environment, and equipment protection. Yeah? And as we progress in this course on control, we will look more and more into multi-variable and constraint control, and for advanced process in the control system. Yeah? In your fourth year later on, yeah? When you learn subject like process control system, we're talking about real-time optimizations, yeah? And how that led to planning and scheduling. So this is the final slide that we covered last week on Friday. Yeah? So we divide the activity on into engineering activity as well as and also information-based activity. So in the circle is the engineering activity. Yeah. So we started with formulating the control objective. Yeah. With the management objective or input there, together with information from existing plants if available for existing plant. Then come up with the process model, develop the process model. So here we use the understanding of the physical and chemical principles, followed with computer simulations and plant data if available. Yeah? And from there we come up with the device control strategy, where for the control strategy we need to know what type of process control theory that you want to apply, be it proportional, integral, derivative, or the combination of these three. Yeah? And we also learn from our experience with existing plants if available. Yeah? And followed also can be done together with computer simulations. Yeah? And with that, we can next we can select control hardware and software together with some information from the vendor, yeah, or the supplier, or the hardware, the equipment, or the software, yeah, for the control systems as well as for the simulations. Yeah? And from there, we can install the control system, and we can also adjust the controller settings accordingly. And finally, we have the final control system. So that is last week what we have covered last week. Okay. So for today's class, for today's lecture, we will look into mathematical modeling. Yeah, you can see my ELIP website, right? All of you can see the yeah, okay. So yeah, I can open this PowerPoint, yeah, on mathematical modeling. So we look into what it actually means with mathematical modeling of chemical processes that can be used in control systems. Yeah. So just some idea what actually means mathematical modeling. Yeah. So basically, mathematical model actually representations of the essential aspect of an existing system or a system to be constructed with which represents knowledge of that system in a usable form. So everything should be made as simple as possible, but actually not as simple as the method actually, because remember in the first lecture, in the lecture last week, we can see that when we develop the mathematical model, we need to come up with certain assumptions. Yeah? Of course, the understanding of the theory or the fundamental with regards to the process, be it additions of heat, for example, that will lead to energy equations. Yeah? Or the understanding of conservation of mass, actually, mass that will lead to the understanding of to the calculations of a mass flow rate or velocity in this case. Yeah? So the general modeling principles, yeah, we're talking about the model equations are at best an approximation to the real process, where we say that here that all models are wrong, but some are useful. Yeah? So the second point here, when you say that all models are wrong, but some are useful, with the view that you come up with a model based on certain assumptions. Yeah. So when you come up with assumptions, that's mean it is good as your assumption. Yeah? So if you come up with a bad assumptions, I guess the models are probably not 100% correct. So that's why it's we say that all models are wrong. Yeah. But nevertheless, based on the assumptions that we made for that particular process, it will be useful. Yeah. At least you will probably, it will be probably not 100% correct, but then we try to make it as accurate as possible. Yeah, so there is mathematical models in this case, and being applied in engineering activities. Yeah? So the third point there, is that modeling inherently involves a compromise between model accuracy and complexity on one hand, and the cost and effort required to develop the model on the other hand. So the process modeling, it can be said as both an art and a science. Yeah? So creativity is required to make simplifying assumptions. Yeah? So we talk about assumptions now. They result in an appropriate model. Yeah? So with our assumptions, we come up with a mathematical model. Yeah? And our assumptions normally are simplified assumptions. Yeah? And how to make our assumptions probably not too simplified. Yeah? And that will determine whether our model is accurate or not. Will be depend on our creativity. Yeah? Of what you understand about the process. So if your understanding of the process is flawed, your model probably quite way off from the accurate one. I mean, the best model probably cannot be obtained, and that probably will lead to longer time for you to achieve your objective in this case. So the dynamic models of chemical processes consist of ordinary differential equations, or ODE, and or partial differential equations, PDE, plus related algebraic equations. Any questions so far? So far so good? Is it too complex for you? As you can see here, as you probably noticed, yeah, when we're talking about the mathematical model, we are actually covering the topic of differential equations, ordinary or partial differential equations. Yeah? And you have learned in algebra in your maths, I believe maths 3. Yeah? That is actually a differentiation with respect to time, and also with respect to the directions. Yeah. So if three-dimensional, will be x, y, z. Yeah. For the unit vector I, j, k. Yeah? I for x, j for y, k for z axis. Yeah. So we look into what actually means with a systematic approach for developing dynamic models. So we need, first of all, when we want to come up with a model of our control system, where this mathematical model represents the process or the physical process to be related to thermodynamics, talking about humidity, or fluid mechanics, talking about the flow. Yeah. We need to, first of all, we need to state the modeling objectives and the end use of the model. And they will determine the required levels of model detail and model accuracy. Yeah. So from there, after you determine the objective, yeah, in other words, what's the purpose of the model, we come up with number 2 there, to draw a schematic diagram of the process and label all process variables. Yeah. So that's why when you try to do your assignments on a pull-out threshold, for example, yeah, for the control systems, I did mention, yeah, if I'm not forgotten, probably you can include a schematic diagram of all the components, yeah, and how the measurement, the data being transferred from one point to another. Yeah, so we make it a bit more interesting by looking into a turbine, perhaps a turbine, which being installed in the middle of the water, yeah, on the river, and then this data will be transmitted to dry land. It's not in the island, probably to the bank of the river. Yeah. So we need to come out a schematic diagram of the process and label all process variables. And from there, we need to list all of the assumptions that are involved in developing the model. And we try for parsimony. Yeah, there is what it means with parsimony is that the model should be no more complicated than necessary to meet the modeling objectives. Yeah? And from there, we can determine determine whether special variations of process variables are important. So if so, from there, a partial differential equations model will be required. Yeah? So this one I mentioned about differential equation, ordinary as well as partial. And from there, we can write appropriate conservation equations. Conservation equations talking about the mass continuity component in X, Y, or Z direction, energy conservations of energy, and so forth. Yeah, there are many other conservation of momentum, etc. Yeah. Then number 6, we need to introduce equilibrium relations and other algebraic equations from thermodynamics. Yeah, from your understanding from thermodynamics, transport phenomena. Transport phenomena is a mass transfer. Yeah, thermodynamics normally with regards to heat or energy. Transport mass. Transport phenomena is the terminology used in chemical engineering when we're talking about mass transfer. Yeah? Chemical kinetics as well as the equipment geometry. Yeah? And from there, we perform a degrees of freedom analysis to ensure that the model equations can be solved. Yeah? So we solve in X direction, Y direction, Z direction, etc. Yeah? And number 8, we need to simplify the model. And when we simplify the model, it is often possible to arrange the equation so that the dependent variables or outputs appear on the left side and the independent variables or the inputs appear on the right side. Yeah? And this model form is convenient for computer simulation and subsequent analysis. Yeah? So we have our point there that we want it. We want that the physical process can be mathematically modeled. Yeah, and when we transfer, when we have a set of output and inputs in the form of equations. Yeah, then we have some sort of matrix form. Yeah, and this can be used for computer simulation and other analysis later on. Yeah. Number 9, we need to classify the inputs as disturbance variables or as manipulated variables. Yeah? So we also need to classify what kind of inputs, whether it's disturbance or manipulated variables. So what is the approach in modeling, the modeling approaches? First, we have the physical or chemical with regards to fundamental or global theory. Yeah. So the model structure by theoretical analysis will cover material or energy balances. Yeah. Material, talking about mass. Yeah. Energy, talking about the equations of heat transfer. Yeah. And then heat, mass, or momentum transfer. And from thermodynamics, we have the chemical kinetics, and as well as the physical property relationships. Yeah. So the model complexity must be determined based on our assumptions. Yeah. So the more complex your assumptions, yeah, the more complex is your model, in other words. And it can be computationally expensive, yeah, and cannot be done in real time. Yeah. And some of these models, yeah, could be expensive or very time consuming to obtain. Yeah. So the results for this model is expensive or time consuming to obtain. Yeah. But what we notice now with the advancement in information technology, as well as our computer system, have become more and more powerful. Yeah. The time consuming probably can be discounted, but as we use a faster and even faster computer, in this case, we ending up with a more expensive equipment. Yeah. For example, a supercomputer, for example, can do a simulations of radioactive decay from Japan all the way to California across the Pacific Oceans, for example. If you use your own desktop, like this desktop that I have here in my office, probably taking me 1 week to do. But with the advancement in computer systems by using supercomputer, here we're talking about a CPU probably as big as the engineering faculty building, for example. In that case, the simulations can be done within maybe half an hour or 1 hour the most, maybe. Yeah. But of course, the system is very expensive, talking about millions of ringgit. Yeah. So even in Malaysia, there are only two places that are having this supercomputer. Yeah. The one that I have visited actually in one in UTP, University Technology Petronas. Even that require the researchers, yeah, to queue or to book the facility to do their simulation, probably 1 month or 2 months in advance before they do the simulations. Yeah. So once the turn come, they can do their simulation for the research work. Yeah, the researchers, the professors having their research students doing some simulations. They will book on behalf of the students. Yeah, and from there they can run the simulations. Yeah. So it's could be very expensive to come up with the system, but then the time will be reduced significantly by using the kind of advanced computer system. Yeah. And also this modeling also can be good for extrapolation, scale up, etc. Yeah. And even at some point, it does not require experimental data to obtain where the data required for validation and fitting. Yeah. So it does not require experimental data to obtain data required for validations and fitting. So this means the computer simulation itself already has their own way to validate the simulation. Yeah? So you can imagine, for example, in Formula 1, motor racing in Formula 1, yeah. So company like Mercedes, Ferrari, Honda, they are a big company, yeah, multi-billion company competing with each other, and they have a lot of money, yeah. So they come up with all those expensive computer, yeah, and do the simulation. So they don't need to do it in wind tunnel anymore. Everything can be done using CFD, for example, computational fluid dynamics. Yeah. So that in that particular system software, they have their own way to validate their own data. Yeah. So basically, It can even change the configuration of the car during the race based on the simulation that they are doing during the race itself. So now we look into what kind of law or conservation law that we have. Yeah, we have normally we have a conservation law, namely the conservation of mass. Yeah, where the rate of mass accumulation is equal to the rate of mass in minus the rate of mass out, and then even from that conservation of mass or continuity equation. Yeah, we also can have conservations in I, J, K directions or X, Y, Z directions. I is using the unit vector in X direction. We're talking about the rate of component I accumulations is equal to the rate of component in I in minus rate of component I out plus the rate of component I produced. Okay. So to that extent, yeah. With regards to conservations of energy, yeah. The conservation of energy talking about the general law of energy conservation, which is called the first law of thermodynamics. So it can be expressed as the rate of energy accumulations equal to the rate of energy in by convection minus the rate of energy out by convection plus the net rate of heat addition to the system from the surrounding plus the net rate of work performed on the system by the surrounding. So therefore, in this case, the total energy of a thermodynamic system for U total is the sum of its internal energy, kinetic energy, and potential energy, as given by equations 2.9 there. Yeah. Any questions so far?
No, sir. Thank you.
Okay. So most of you can follow me?
Yes.
Okay, great. What we are doing now is a very fundamental. Yeah. Basically, what we try to do, in other words, we apply what you have learned in thermodynamics, fluid mechanics, as well as your good understanding in mathematics, especially on algebraic, on a vector, in your maths 1, 2, 3, and 4, yeah, and come up with mathematics modeling, yeah, and from here we're talking about the simulation. So here we're talking about empirical value, or in other words, known as the black box, where we have large number of unknown parameters, and it can be obtained quickly, for example, through linear regressions. And normally the model structure is subjective, but nevertheless, probably it's not appropriate to extrapolate it. Then we also have the semi-empirical. There is the compromise of first two approaches, where in this case the model structure may be simpler, and where typically 2 to 10 physical parameters estimated with non-linear regressions, and it has a good versatility and can be extrapolated. And this actually leads to the concept of real time, because for semi-empirical it can be run in real time. Right? For linear regressions, we have equations of y equal to CO plus C1x plus C2x2. Yeah, so it's a curve which means x2 there. And then for non-linear regressions in the form of y equal to k constant times 1 minus 2 to the power of minus 3 over 2, for example. Yeah? So this is talking about the log, the ln or log. Log that means ln of 10. Yeah? So the number of parameters affects accuracy of model, but confidence limits on the parameters fitted must be evaluated. So therefore, the objective function for data fitting is to minimize the sum of squares of errors between data points and model predictions, where we use optimization code to fit parameters. And non-linear models such as neural nets are becoming popular, and that will lead to automatic modeling. So we actually use the mathematical modeling. In short, we are using mathematical modeling for first to improve understanding of the process. Yeah? So it could be a thermodynamics or fluid problems or related with energy. So from there we come up with the energy equations. We're talking about energy or talking about the flow, part of the Bernoulli equations, momentum equations, for example, the conservations of energy. So basically that's improve the understanding of the process. So the second, to optimize process design or operating conditions. And thirdly, to design a control strategy for the process. Remember, we're looking to the hierarchy of process control. Yeah. And fourthly, to train operating personnel. Yeah. So there is the users of this mathematical modeling. Yeah? So imagine, for example, the fourth point, you are given NSYS and you are asked to do computational fluid dynamics based on fluent in axis. Yeah. So instead of just key in the number there, by right, in order for you to explain your simulation result in fluent axis in regards to flow, velocity profile, etc. If you know what is the equations behind that simulations work, they've been used by the computer to do the simulations work, yeah, you will be able to explain, perhaps you can explain the results more clearly and more convincingly. Yeah? So that means the training the operating personnel in this case. Now we look into some of the examples, illustrative examples in developing dynamic models. So we look back into our blending process, how we model it. Yeah. So remember our third tank blending process that we discussed last week and which I reviewed with you earlier on. Yeah. So we have liquid coming in with different concentrations X1 and W1 mixed with another fluid component X2 W2 inside the blending tank. Yeah. And from there we have the output X and W. Yeah. So we look into the mathematical modeling for this. The first one, the assumption, we say that the rate of accumulations of mass in the tank equal to the rate of mass in minus the rate of mass out. So this is our assumption. Yeah. Here we can simply say that we do not consider leakage, for example. Leakage, maybe the tank got a hole on it and the thing is not come out as X and W, but some other due to leakage it come out with some not follow this conservation of mass, for example. Yeah, not to mention, for example, liquid loss due to evaporations, maybe, especially if this tank being heated up to certain degrees, for example. Yeah, if the steam escape, basically the mass to reduce over time. Yeah. So from here we have the equations, the mathematical equations that d v rho over dt equal to w1 plus w2 minus w. Yeah? So in other words, we take w equal to w1 plus w2 in our standard equations. But here, because talking about it is a process, so we're talking about the change with regards to time as equal to w dv rho rho over dt equal to w1 plus w2 minus w. So w1, w2, and w are mass flow rates. Yeah? And the unsteady state component balance is given by dv rho x over dt equal to w1 x1 plus w2 x2 minus wx. And the corresponding steady state model was derived, was given by that equation. Everything moved to the right hand side from left hand side to right hand side. So on the left becomes 0. Yeah. So that is considered as or named as the steady state model. Equation 2.4. Yeah. There is 0 equal to W1 bar plus W2 bar minus W bar. And then when we also considering the concentrations, yeah, it becomes 0 equal to W1 bar, the product of W1 bar times X1 bar plus W2 times bar times X2 bar and minus W bar times X bar, which is 2.5. So if we revisit equation 2.2 and 2.3 from last week lecture, so now we are applying the differential equation to it. So rho density, rho especially is a constant, so I take it out from that derivative dV/dt. So we apply out of that equation. So rho dV/dt equal to W1 plus W2 minus W. Yeah. And with regards to construction X, we have rho dVx dt equal to W1 x1 plus W2 x2 minus Wx, equation 2.13. So equation 2.13 can be simplified by expanding the accumulation term using the change rule for differentiation of a product. So in this case, we have the equations being further expand to become rho dx over dt equal to rho v dx dt plus rho x dv dt. Yeah, equation 2.14. And by substitution of equation 2.14 into 2.13, that will give you expanded equation of rho v dx dt plus rho x dv dt equal to w1 x1 plus w2 x2 minus wx. And by substitutions of mass balance in equation 2.12 for rho dv dt in equation 2.15, that will give you equation 2.16 is rho v dx dt plus x times W1 plus W2 minus W equal to W1x plus W2x2 minus WX, equation 2.16. And cancelling the common terms and rearranging equation 2.12 and 2.16, so a more convenient model form obtained as dV/dt equal to 1 over rho times times W1 plus W2 minus W, and dx dt in the x direction, so W1 over v rho times x1 minus x plus W2 over v rho times x2 minus x, equation 2.17 and 2.18 respectively. So we can see here, figure 2.2 here, the exit composition responses was stirred tank blending processes to step changes in flow rate W1. That's given by B there, in the middle, then flow rate for W2, yeah, in C, yeah, the middle there, B and C in the middle. And then for flow rate W2 and inlet composition X1, E in the top there, and normalized response for parts B and D, which is the figure at the bottom there, E, yeah, the normalized response. So there is one example. We can also further enhance this. Instead of just looking into the volume or the mass flow rate, we can also include perhaps like temperature, for example. So if you temperature, then in this case, we will expand the equation to include the energy equation in a way to make it a bit more complex in this case. Yeah. For example, if you consider heating process, for example, probably you need to have assumptions such as number 1, for example, we have perfect mixing, and therefore the exit temperature T is also the temperature of the tank content. The liquid flow out V is constant because the inlet and outlet flow rates are equal, so we do not consider evaporations in this case. Number 3, the density rho and heat capacity C of the liquid are assumed to be constant, thus here temperature dependence is neglected. And number 4, heat losses are considered to be negligible. So in this case, for the processes, an example considered in this topic on algorithm learning, yeah, it is appropriate to make 2 assumptions. One is that the changes in potential energy and kinetic energy can be neglected because they are small in comparison with changes in internal energy. Yeah? And the second assumption is that the net rate of work can be neglected because it is small compared to the rates of heat transfer and convection. So for this reasonable assumption, the energy balance in equation 2.8 earlier can be written as du internal, the internal energy, over dt equal to minus the diff of W h bar plus Q. Yeah. So U internal is the internal energy of the system. H bar is the enthalpy per unit mass. Small w is mass flow rate. Q equal to the rate of heat transfer to the system. The triangle there denotes the difference between the outlet and inlet conditions of the flowing stream, and therefore minus if there W H bar equal to the rate of enthalpy of the inlet stream minus the enthalpy of the outlet stream. S there because it could be more than one stream, yeah? More than one inlet or outlet in this case. Okay, so basically when you use software like Fluent, for example, in the methodology of Fluent, yeah, or other CIV software like Star City perhaps, or Phoenix maybe, yeah, you're always being given this kind of equation. This is very, very brief because the triangle itself is a combination of both the inlet and outlet, the difference. Any questions? Okay, we can move on. Sounds a bit complicated. Of course, it's complicated because we're talking now the computer language. When we do the simulation using computer, so now we're talking about the computer language, which represents the equation or the models in this case. But once in a computer, then we don't care because the computer, this model being interpreted into the computer language. We look into examples, model development 1. Yeah. So for a pure liquid at low or moderate pressure, the internal energy is approximately equal to the enthalpy. So the internal energy U internal equal to the enthalpy H, and H depends only on temperature. Consequently, in the subsequent development, we assume that the internal energy U equal to H and U bar internal equal to H bar, where the caret, not bar, is the caret. So caret means per unit mass. So as shown in the book in Appendix B, which I have here, a differential change in temperature dT produces a corresponding change in the internal energy per unit mass d U caret internal. Yeah, so d U caret internal equal to d H caret equal to C dt. Yeah, C is actually the constant pressure heat capacity. So it's after other differentiation. dt is a constant, just like the density now rho. Yeah? So the total energy, the total internal energy of the liquid in the tank is given by U internal equal to rho V U caret internal equal to 2.30. In case of second model development 2, where here we have the an expression for the rate of internal energy accumulation can be derived from equation 2.29 and 2.30. Then you have du internal over dt equal to rho v2 dt over dt. Yeah. So this is this term appear in the general energy balance. Yeah. And suppose that the liquid in the tank is at a temperature T and has an enthalpy H caret, and integrating equations 2.29 from a reference temperature T ref to T will give you H caret minus H caret reference equal to C times T minus T reference. Yeah, where H caret reference is the value of H caret or T reference, and we had loss of generality. We assume that H caret reference equal to 0, and therefore equation 2.32 there. Yeah, H caret minus H caret reference to the C times T minus T reference can be rewritten as H caret equal to C times T minus T ref only. Yeah, so we get rid of the H caret reference there. Yeah. So the third model development 3, where here we're talking about the inlet stream given by H caret I equal to C Ti minus T reference. Yeah, talking about the I direction. Yeah. So substituting equation 2.23 and 2.24 into the convection term of equation 2.10, they give you equation 2.35 here. Yeah, and we substitute back equation 2.31 and 2.25 into equation 2.10, we have these general equations of B rho C dt over dt equal to W C T I minus P plus Q, 26. And look at the equations when we define deviation variables. There is a deviation from the set point. Yeah, we have y equal to t minus t bar, where t bar is the desired operating point. Then u equal to ws minus ws bar, where w bar s and t bar from the steady state. Then from the equation, rho v over w times dy dt equal to minus y plus theta hv over dc u. Yeah, noting that delta hv over wc equal to kp and rho v over wc, so 1. And dy dt, when dy dt equal to 0, yeah, then we have y equal to kp u, and so 1 dy dt equal to minus y plus kp u. Yeah? And that will give you the general linear ordinary differential equation solutions. There is the sum of the exponentials. That is when we have u equal to 1, the unit step response. Then we have y t equal to kp times 1 minus e to the power of minus p over so 1. So this is how it looks like, the step response of a first order system and graphical constructions used to estimate the time constant tau. Yeah. So at so 1, 2 tau, 3 tau, 4 tau, every and become steady again. We will reach at 5 tau. So this is some of the real examples with the real value of t or t bar, delta h, for example, they given the value. In that case, you can calculate actually what is the time constant tau. Yeah? For example, here tau is equal to 2 hours, for example, and that we replace in the equation. We have this kind of equation. Yeah? So we have this equation with respect to dy dt, y, e, etc. Yeah. So that's the point. So the y represents t minus t bar, for example. U represents ws minus ws bar, for example. So dynamic model. And if you have the boundary conditions, then you can further reduce equations to find the value for t, for example. Yeah. Or u maybe, etc. Yeah. So in this case, when we have this kind of equation, then now we can have what's called process dynamics, yeah, which is inherently concerned with unsteady state behavior or the transient response or process dynamics. Yeah, so we are looking now into what's called the process dynamics. Yeah, so from this kind of equation, this one here is now this one here, the dynamic model. Yeah, this dynamic model we have the process dynamics. Yeah, process dynamics. So remember we briefly discussed about lag the other day, about lag. Yeah? So even in the process of stirring the water inside a tank, yeah, using a heater, yeah, if there are lag between heating element temperature and process temperature, then we have the heat transfer limitations of HE times A TE minus T. So therefore, in this case, energy balances will be changed accordingly. Yeah. So this is when talking about lag. Yeah. Because when you heat something, the whole liquid body or the fluid body will not reach that particular temperature instantly, but they take some time for it to reach the temperature, the body temperature. Yeah. In this case, yeah. So it's a function of QI, H, etc. So in this case, and they're also probably including the disturbances to input, for example, in the process. But it's a manipulated variable to input and the control variable to output such as the disturbances. So numeracy for multiple input, multiple output, or single input or single output. So from there, actually, we come up with the degrees of freedom analysis. So we can list all quantities in a model. They are non-constants or parameters that can be specified on the basis of equipment dimensions. non-physical properties, etc. Yeah? And we can also determine the number of equations NE and the number of process variables NB. And we note that the time t is not considered to be a process variable because it is neither a process input nor a process output. And we can calculate the numbers of degrees of freedom NF equal to NB minus NE. And we can identify the NE output variables that will be obtained by solving the process model. And we can identify the NF input variables that must be specified as either disturbance variables or manipulated variables in order to utilize the NF degrees of freedom. Yeah. So if the degrees of freedom analysis for the stirred tank model, yeah, the three parameters for this stirred tank model is actually the volume V, the density rho, and the constant C. Yeah. And the four variables, the three parameters and the four variables are the temperature T, Pi, W, and Q. And the equations actually represented by only one equation, equation 2.36. Yeah. So you can see that all the parameters and the variables being joined only in one equation, equation 2.36. Yeah. So from here you can say that the degrees of freedom, or NF, given as 4 variables minus 3 parameters, 4 minus 4 variables minus 1 equation, this means the degree of freedom is actually 3. Yeah. So the process variables are classified as one output variable T and 3 input variables Pi, W, and Q. And for the temperature control purposes, it is reasonable to classify the 3 inputs as well as the 2 disturbance variables Pi and W and the multiplied variable Q. Yeah. So this is one thing. Yeah. You can also look into examples like on biological reactions, for example, but I will not cover it here because it's more appropriate for chemical engineers or in chemical engineering. So we not look into that. So I do not expect you to know what is enzyme, etc. For example. And we not study about enzyme in our discipline, mechanical engineering, but more on the flow, biomass, energy, etc., but not enzyme, cell growth, etc. Yeah, so we not consider this. Yeah, but the concept is more or less the same. Yeah, the approach is the same. Come up with the assumptions, come up with the mathematical modeling based on the theory. Yeah, and we further simplify into this order. Any questions? So you can follow so far. It's a bit complicated, but I can say that as if I try to explain to you what is Fluent is doing in NSYS. That's it. Yeah. So it sounds complicated, but this is what I try to do now, as if I try to explain to you how that Fluent simulations being done in NSYS. Yeah, Fluent NSYS in this case. So you have that nice picture of the simulations results. So basically, we try to explain how it's being produced, what kind of mathematical model being used, the assumptions, etc. Yeah. So that's why a lot of processes, especially turbulence flow, for example, people still doing a lot of simulations work on it because the assumptions from one researcher to another probably different. Yeah. Because the physical process probably is slightly different from the previous one. Yeah. And also maybe in terms of their boundary condition will be changed. Last time they used to simulate things big, but now people tend to use the simulation for small things, for example. Yeah. Any questions? It's already 3 o'clock. Okay. If no questions, can I leave you here and then we continue again on Friday morning, 10 o'clock. Yeah. And from that, then maybe this time around, because we cannot meet face to face, I give you a bit like a tutorial you can do during the weekend. Yeah. And then that will help you to do your assignment as well, which will replace your exam. Yeah. I will give you one more assignment. Yeah. only the assignment will represent the exam question, your final exam question, and you will only be able to do it in 1 week. Yeah, most likely by 20th of July until 27th of July, right? 1 week window. So before you see the question on 30th of July, we discuss it now. Yeah, so we do that on Friday. Yeah. So I will close this one. Let me see this one. Okay. You can see the Ellipse website, right? Yep. Okay. So basically that. So somewhere in we will not have group project presentations anymore, but somewhere in week on week 13 basically or 14, we, myself and Dr. Fikri will put up that assignment questions for you. So there'll be one assignment for me, which will cover on topic on control, including numerical modeling. Yeah. So Friday we continue on numerical modeling, but we look into some on how to derive it. And next week we look into transfer functions. So that will involve Laplace transformations. Yeah. Any questions?
No, sir. Thank you.
Okay. If none, then I can leave it here, but we are on the attendance again, in case you need to take the attendance. And take your attendance if you haven't done so. If any questions, you can post it in the WhatsApp group, because I will leave the room to join them in the faculty meeting room for some preparations for tomorrow webinar with the Petronas Tarigani CEO. Okay.
Thank you, sir. I hope you have a good evening.
Okay, good. Good day to you too. So see you all on Friday. Yeah? I joined the dean and the other deputy deans in the faculty meeting group. Yeah, to get ready for webinar seminars with the Petronas Tarigani CEO tomorrow. Yeah.
All right, sir.
See you on Friday, and I guess you will all enjoy the talk tomorrow.
All right. Thank you.
You all will be invited, right?
Yes.
Yeah, correct.
It's a compulsory.
Oh, okay. Okay, it's supposed to be my first event. Taking over from Dr. Lim Sokong industry management, but I let Dr. Lim to handle it until the end.
Ah.
Yeah, okay.
All right.
Friday then.
Good luck, sir.
Thank you.